Now I'm going to start the Langevins theory of susceptibility calculation for diamagnetic materials. Students, I told you in the previous class also, the substances which are having even atomic number, substances having even z, even atomic number, all produces comes under the category of diamagnetic material. Comes under diamagnetic. You may ask question, what happens that is? If there is atomic number is even, then electron pairing is there. One is spin up and another one is what? Spin down. Like so that the net spin angular momentum is equal to 0. When net spin angular momentum is 0, then magnetic moment contribution due to spin angular momentum is also what? 0. One is with spin up and another one is what? Spin down. So the net spin is what? 0 in case of what? Diamagnetic material. Now you ask question, sir, anyway that is magnetic field is produced by two motion. One is orbital motion and another one is what? Spin motion. For spin motion it is 0. For spin motion m equal to what? 0. m1 equal to what? 0. What about orbital motion? But this orbital motion also, what happens is, one is clockwise direction and another one is what? Anti-clockwise direction. This m2 is also what it is? 0. Or in some cases it is very minimal value. The spin orbital motion, magnetic moment due to orbital motion is very low. So that almost it is m2 is equal to 0. That means net magnetic moment m1 plus m2 equal to what? 0. This is the situation in absence of external magnetic field. In absence of external magnetic field. I think you understood this. What is important is, all diamagnetic materials are having the what? Even atomic number, even z. Where there is a spin motion, that is what? There are two kinds of motion is there in the electron. One is orbital motion and another one is what? Spin motion. As I told you, that is spin motion is where electron pairing is there. One is spin up and another one is what? Spin down. So the net spin angular momentum equals 0. So the contribution of magnetic field moment is also what? 0. What about orbital motion? This value is also very close to 0 here. That's why I am writing here m2 equal to what? 0. Net m equal to what? 0. This is the situation in case of what? In the absence of external magnetic field. But situation is different when there is a applied magnetic field. When the magnetic field is applied, what happens is, there is a magnetic momentum is there. Please note down this. When diamagnetic materials are subjected to external magnetic field, there is a induced magnetic momentum is there. Induced magnetic moment is produced. Induced magnetic moment is produced. When it is produced here, when it is subjected to what? External magnetic. If you remove it, this also becomes what? 0. It is as good as the students perfectly they are aligned as long as teacher is present in the classroom. If once teacher is absent, again all students will be aligned in what? In the random direction and all that. And another important thing is, here always the magnetic momentum is produced because of change in velocity of the electrons. There is a change in velocity. When there is a change in velocity, there must be what? Acceleration. When there is an acceleration, there must be force. That force it is because of what? Induced EMF and all that. It's all these things I explained in the previous video, probably in the fourth video, and all that I would have explained all these things. And don't bother much about this. Now I will start with what? The derivation for the Langevins theory of susceptibility calculation for diamagnetic material. At least you write something, you should know that. Here, what is that? The diamagnetic material is exhibited by only which kind of elements? Elements are having the what? Even atomic number. Z is what? Even and all that. Where in the absence of external magnetic field, the net magnetic momentum is what? Zero. Sir, what about the situation when I apply the external magnetic field? Then there must be what? Induced magnetic momentum is what? Produced here. This induced phenomenon is produced, magnetic momentum is produced. It is because of what? There is a change in orbital velocity of the electron and all that. Now, and one more thing I'm using here. Suppose this is the origin here, origin. This is the position coordinate. This is the position coordinate. Here, this is R1. What is the component of this along x direction? Here, x direction specifically why I'm taking is, in this direction, magnetic field is what? Applied. The component of R1 along this direction equal to R1 into what? Cos theta. This is the component of position vector along the direction of the what? Magnetic field. This term I'm using while deriving the equation now. Okay. Now derivation begins now. Here, additional magnetic momentum is produced in the material. This one I will call it as a what? Delta M. What is delta M? Delta M is the additional induced magnetic momentum is produced here. It is because of what? The Larmor frequency and all that. I don't want to create a confusion and all that. Delta M equal to minus E square R square B divided by what? 4 into what? Yeah, that's the equation. Here there are several electrons are there. Each electron will produces the additional magnetic momentum, so that here there is a total magnetic momentum delta M equal to this one. E square B divided by what? 4M into what? Ri square with what? Negative sign. Why I am writing here? Because how many electrons are there? Z number of what? Electrons are there. So that the total magnetic momentum is what? That I am taking the what? The position, summation I am taking here, this one. Here the variable quantity is what? I only, where I equal to 1 to what? Z. Can I write like this? Delta M equal to minus E square B divided by what? 4M. Divided by 4M. Summation of what? I equal to 1 to what? Z. Here, can I write Ri square into what? Cos square theta. Because Ri is a position vector. Already I told you, Ri bar equal to Ri into what? Cos theta. It is a component of this. Now, now here like this. Here M equal to this. M equal to for n number of this one n into what? E square B divided by what? 4m. What is m? This difference is what? For n number of atoms here. That's why delta m, it is for, I am writing what? M equal to, I am removing the summation sign. I am multiplying what? N. N is the total number of what? Atoms. N E square B divided by what? 4m into what? This quantity. Ri square into what? Cos theta is. Now this quantity is 2 by 3 of what? R square. This you have to remember that. Now this quantity is what? Get cancels. Then what is left is m equal to minus n into what? E square B divided by 3 into 2 what? 6. 6 into what? M of what? R square. But in the previous class we know that B not equal to mu naught into what? H, we know that. Now I am substituting m equal to minus n e square mu naught into h divided by what? 6m of what? R square. But m by h equal to what? This is m by, this term I am taking here, m by h equal to minus n e square mu naught divided by what? 6m of what? R square. What is this quantity? M by h is nothing but what? Susceptibility equal to minus n e square mu divided by 6m of what? R square. This is susceptibility. Students, you see, the difference between the previous derivation and this derivation is the susceptibility of all that is susceptibility or magnetic momentum is independent of temperature for the diamagnetic material. It is independent of temperature for the diamagnetic material. But for the paramagnetic materials, that is susceptibility, it is purely, it depends upon the temperature, where in paramagnetic, here as temperature increases, susceptibility is what? Decreases in paramagnetic. But for the diamagnetic material, it is independent of temperature. And one more thing, what is the significance of this negative sign is, if magnetic field is applied in this direction, applied magnetic field is H is like this. But atomic magnets, magnetic momentum is aligned in opposite direction. This is the situation in case of what? Diamagnetic. This is what this negative sign is represents. But in case of paramagnetic material, it is like this. If applied magnetic field is like this, here all your atomic magnets, they are oriented with respect to what? H in the same direction it is arranged. This is the situation in case of what? In case of paramagnetic material. It is paramagnetic. This is the situation in case of what? That is what this negative sign represents. Remember, lastly, diamagnetic material is what? Independent of temperature, but paramagnetic material, it is not like that. As temperature increases, the thermal agitation is increases. As thermal agitation increases, these dipoles, they will not orient in the same direction. They will start for orienting in what? Random direction. As a result, M decreases. As M decreases, then susceptibility is also what? Decreases. Okay, now stop it.